So we're going to hopefully build off of that stuff that you learned in Chem 101. So thermodynamics. This is totally different from kinetics. So earlier in the year, we talked about kinetics, and kinetics is about how fast a reaction was going to go. And that's all about this activation energy barrier, right? So the speed of a reaction is 1000% related to that activation energy barrier. Thermodynamics does not look at that at all. Thermodynamics just looks at the stability of the reactants and the stability of the products. And it says, which is favored. So if we look at this endothermic reaction, the reactant side are more stable, lower in energy than the product side. So it doesn't look at how fast the reaction is. That has to be studied separately. So this is all about just energy, nothing about speed in this chapter. Review of enthalpy. So you guys should have learned some enthalpy back in Chem 101. Enthalpy is a fancy word for heat as long as pressure is held constant. If pressure is not held constant, it is my understanding from people that are far smarter than me when it comes to this physical chem stuff. It is my understanding from talking to some people, again, far smarter than me when it comes to this stuff, that enthalpy has no physical meaning if pressure is not held constant. But if pressure is held constant throughout the duration of a reaction, then enthalpy is just heat. So constant pressure, enthalpy. So when you hear the word enthalpy, I am 100% okay with you just thinking of the word heat. Okay. So change in enthalpy, essentially change in heat for a chemical reaction. If a reaction has a positive change in enthalpy, that's an endothermic reaction. Energy or heat is going to be absorbed by the reaction. It would feel cold to the touch because it's stealing your heat. An exothermic reaction, one with a negative delta H, that's one where heat is exiting, right? And if you touch it, it would feel hot because it's warmer than you are. So you're going to feel it is going to feel warm. One of the three ways, and again, you should have learned 3 ways in Chem 101 to find enthalpy. One of those 3 ways should have been this method, where you use standard enthalpy of formation values. So this formula is going to be really important. We're just going to swap out the H's for S's and G's here as the night progresses. It's a really important formula, and it's written in math speak, so at first it's kind of intimidating. But it's saying the change in enthalpy for a reaction under standard conditions, that little degree sign means 25 degrees Celsius, 1 atmosphere of pressure, and 1 molar for aqueous solution. So if you got a gas, it's got to have a partial pressure of an atmosphere. If you got a solution, it's got to have a concentration of 1 molar. And thermodynamic standard conditions is 25 degrees Celsius. So once again, that's 25 degrees Celsius, 1 molar for aqueous solutions, and 1 atm for gases. So that's what that little degree sign means. So change in enthalpy under standard conditions is equal to the sum. That's a mathematics, sigma means sum. The sum of the standard enthalpies of formation for each product times the coefficient in the balanced chemical equation for each product, minus the sum of the standard enthalpies of formation of the reactants times their coefficients. So let's practice one of these, right? Okay, let's try and find the change in enthalpy for this reaction right here. And the first thing that I want to mention to you is that these change in enthalpies of formation values tell you how much it takes to form that substance, how much energy is released when you form that substance. 1 second here. Those values tell you how much energy is either absorbed or released in the chemical reaction to form that substance from the pure elements. So pure elements like oxygen, they do not have a standard enthalpy of formation. If you look, I did not list O2 gas. Why did I not list O2 gas? Because that's oxygen's pure elemental form, and pure elements have a standard enthalpy of formation of 0, so they don't have to be listed, okay? So what are we going to do? We are going to add up the change in enthalpy of formation of these products, and we're going to subtract that from the change in enthalpy of formation of these reactants. And remember, since oxygen is a pure element, it doesn't go into the equation. So I want you to try that. You are going to multiply these values by these coefficients. Why don't you try to write it out, see if you can get one of these, and I'll do it on the board behind me. Go ahead. I got negative 2,734, which is letter E, folks. Hopefully yours is looking like this. It's going to be 4 right, times the standard enthalpy of formation of carbon dioxide, negative 393.5, plus 6 times the standard enthalpy formation of liquid water, negative 285.8, minus 2 times the standard enthalpy of formation of ethanol, plus 6 times the standard enthalpy of formation of oxygen, which is 0. And if you put that in your calculator correctly, you should hopefully get negative 2,734. How many people remember doing that in Chem 101? Give me like a hand or a thumbs up, or how many people? John remembers it. James, oh, that's so good. That's great, people. This is awesome because boy, are we going to be doing a lot of this. Okay, so that's good. Good, good, good. Hopefully that was review and it went well because man, this is like a one-trick pony here. We do the same thing for entropy and all that stuff, as you'll see here in a moment. Let's keep reviewing. So some graphs, hopefully you got some of these graphs back in Chem 101. Which of those reaction coordinate diagrams, there's a fancy term for that, which of those is an endothermic reaction? And hopefully you picked B, reaction 2. The products are higher in energy than the reactants. That's what makes that endothermic. Reaction 1 is exothermic. Products are lower in energy. Energy will be released, negative delta H. Reaction 3, also exothermic. Products are lower in energy than the reactants. It does have a reaction intermediate in it, but overall it's an exothermic reaction. Here, positive delta H. Products are higher in energy than the reactants. We already just talked about that. Endothermic reactions have positive delta H's. Think of heat as a reactant. That's important for tomorrow's exam, right? That old Le Chatelier, right? So remember, if you have a positive delta H per reaction, you're going to put heat on the reactant side, and then it's add away, take towards. And if you have an exothermic reaction or a negative delta H, you would put heat on the product side, and again, it's add away, take towards. So cool. Spontaneity, folks. What determines whether or not a reaction will happen on its own without an outside input of energy or additional energy from whatever conditions you are at? At first, you may think that all exothermic reactions, reactions with a negative delta H, would be spontaneous, and that no endothermic reactions would be spontaneous. And that is almost entirely true. Let me talk about that logic or line of thinking that I just went over there. So if we look here, this is an endothermic reaction. The products are less stable than the reactants. So why would the molecules want to become less stable? So you would think that endothermic reactions should never be able to happen on their own. And that's what it means to be spontaneous. You probably already know that. So if you're spontaneous, the reaction is going to happen without any outside intervention, right? You don't have to put any energy in. You might think that exothermic reactions are spontaneous all the time. Now, if they have a huge activation energy barrier, right, their kinetics might be really slow. But we're not worried about that. Okay, you might think that exothermic reactions, because the products are more stable, lower in energy than the reactants, you might think exothermic reactions are always spontaneous. And that tends to be the case, but I can give you some examples of endothermic processes that are spontaneous. So what are some examples of that? Well, how about ice melting, right? So a lot of these are phase changes, okay? But let's think about this. If I put a block of ice out on this table here that my computer's sitting on, okay, that is an endothermic process. In order to melt something, you have to put energy in from the environment, okay? So the ice cube is going to absorb energy from the surrounding. That's endothermic. But that happens on its own. Happens completely spontaneous. Like I don't have to, just at room temperature, that ice is going to melt. Here's an incredibly interesting one. Water evaporating, right? Okay, water does not turn from liquid to gas until its boiling point, which is 100 degrees Celsius. Now, this room is hot because this is the room above my garage, my goodness. But it's not quite 100 degrees Celsius up here. And yet, this water, if I leave it sit here, will evaporate. If I come back next week, okay, it's going to be essentially all gone. Because I'm telling you, it's hot up here. Okay, so how does that happen? Right? Okay, how does water turn into a gas? Okay, number one, below its boiling point. And number two, it does it on its own. That's spontaneous. Dissolving salt in water. sodium chloride. Now, some ionic compounds, some salts, when you dissolve them, it's exothermic, and some salts, when you dissolve them, is endothermic. Sodium chloride is one of those salts where the temperature will decrease. So if you drop table salt in here, excuse me, and you have a thermometer, okay, the temperature will go down. It'll get cold, okay? Um, and yet, I wouldn't have to stir it. I wouldn't have to put out any outside energy. If I dump table salt in here, eventually over time, now, it might be slow, but eventually over time, that salt will dissolve and get pulled into solution. So there's an endothermic reaction that is spontaneous. So it can't just be enthalpy. Enthalpy cannot be the only factor that determines whether or not a reaction is spontaneous. Obviously, enthalpy is a major factor because there aren't a whole lot of reactions that are endothermic and spontaneous. Okay, so what else is at play? Well, the other thing that's at play is this second thermodynamic factor called entropy. And entropy is the measure of randomness or disorder in a system. And if you stop and think about each one of these events, in each one of these events, the molecules are having an increase in entropy. They are becoming more random and more distorted. Why? When you go from the solid to liquid phase, you go from, especially if it's water, you go from a lot of hydrogen bonds, locking everything into a nice, rigid, repeating pattern. And then when it melts, the molecules now are not locked in this, or they're more random, right? They can flow. There's still some hydrogen bonds, but it's not this locked in lattice. So the molecules have become more random. They had an increase in entropy. Same thing with water evaporating. If I go from water in the liquid phase to steam, the particles go from being connected to one another to now being all on their own, flying around all randomly. Sodium chloride, when it dissolves, okay, you go from having an ionic compound with a locked-in crystalline lattice of cation, anion, cation, anion, cation, anion, right, in this cube of ions. And when it dissolves, water rips that crystalline lattice apart, and the water molecules wrap themselves around the ions, creating those ion dipole interactions. And now the sodium chloride particles are more randomly distributed throughout the solution than they were before, trapped in these crystalline lattices. So it has to do with the randomness or disorder of a system. So entropy is a measure of the randomness of a system. Okay. And you have to think about both the enthalpy, okay, what are the energy of the reactants, what are the energy of the products, and the entropy, how disordered are the reactants, how disordered are the products. It's those two things that factor together to determine spontaneity. So let's practice this. The second law of thermodynamics, you may have heard of it, is the one that deals with entropy. Entropy is abbreviated with a S, so change in delta S is change in entropy. If a system is becoming more random, more disordered, we say that's an increase in entropy. We assign it a positive value. If a system is becoming more ordered, less random, so if I'm making bonds or I'm locking things into a certain position, we give that a negative delta S value. You can often look at a reaction and predict whether or not it's going to be a positive delta S or a negative delta S. For example, let's look at the Haber-Bosch reaction. In the Haber-Bosch reaction, when this reaction occurs, we're taking 4 gaseous particles, 1 plus 3, 4 gaseous particles, and now we're locking it down to 2. So if you stop and think about this, this is going to have a massive decrease in entropy. We're going to have a negative delta S here. Why? I want you to imagine having 4 playing cards, right? Like a 10, a jack, a queen, a king, right? If you shuffle those 4 playing cards up, there are a lot of different options, right? So I could go 10, jack, queen, king. I could go jack, queen, king, 10. I could go jack, king, queen, right? I mean, I could go king, queen, jack, 10. I could go king, 10, jack, queen. Many, 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 many options, right? And essentially what I'm doing is I would be taking 4 playing cards and all the randomness of that down to 2 playing cards. So imagine if I just had a king and a queen. Well, now there's way less options, right? I mean, if I shuffle up a king and a queen, it can be king, queen, or queen, king. So I go from having a whole bunch of options. Maybe somebody's really good at statistics. They could tell me how many options that would be. But anyway, yeah, what would that be? 4 plus 3 plus 2 plus 1. I don't know. Anyway, forget that. I couldn't care less. So you can hopefully see how if we go from a lot more gaseous equivalents to start down to less gaseous equivalents, we're making the system more ordered. We're bringing stuff together, and there's going to be less option for randomness. If we take a look, so that's a synthesis reaction. If we take a look at this decomposition reaction, the opposite is going to be true. We have 2 gaseous particles going down to 3 gaseous particles. This system is becoming more disordered, more random. That's going to be an increase in entropy, positive delta S. All right. Take a second here. Of those 4 reactions, which one would show a decrease in entropy? Think about it. Look at the states. Okay, so like the gas phase is way more random than the liquid phase, and the liquid phase is way more random than the solid phase, and the aqueous phase is way more random. So anyway, think about that. Which of those 4 reactions would have a absolute positive decrease in entropy? One of them you wouldn't know, but the other one, take a look at it. All right, so let's go down through these. If you look at letter A, we're going from liquid to gas. That's an increase in entropy, not a decrease. That system becoming more random. Take a look at B. This salt is dissolving. That's definitely becoming more random as well. We're going from one, locked in crystalline lattice to 2 ions. If we take a look at C, C you could not predict, I would argue, without looking up. So we have 2 gaseous equivalents on the left. We have 2 gaseous equivalents on the right. It might be a decrease. It might also be an increase. This gets into something called molecular complexity. Excuse me, molecular complexity. We're going to get to that in a minute. Could not predict it without looking at a chart. But if you look at D, we're going from 2 gaseous equivalents down to 1, and that is absolutely positively a decrease in randomness, a decrease in entropy. And that system's become more ordered. There's a negative delta S there in letter D, which hopefully is what you want. All right, folks, remember how I told you that this formula is going to come back? We're just going to replace the H's with S's and then G's. Well, here it is. So how do you determine the change in entropy or randomness in a reaction? Well, you use the change in entropy formula, which says the change in entropy of a reaction under standard conditions equal to the sum of the standard or the entropy of formations, standard entropies of formations of the products times their coefficients, minus the sum of the standard entropies of formation of the reactants times their coefficients. Now, I want to show you where to find these things, right? So I don't think it's Appendix 2B anymore, but I'm going to show you where to find these values in the textbook, because when you get to the homework, you're going to have to look up some of these values. So if we go to the textbook, let me show you. We're going to pull them right out of the textbook because I want you to see how this is done. If you go to the textbook, you'll find a whole bunch of beautiful stuff, right? But we want Appendix G here, the standard thermodynamic properties of selected substances. Yeah. And you're gonna find a big old chart of a whole, I don't need any study tools. No, thank you. You're gonna find a big old chart of stuff, right? So let's first take a look at the top here. At the top, the first column is change in enthalpies. So if you need enthalpy values, that's where you're gonna go to. The middle column we're gonna get to in a moment. Those are Gibbs free energy values. What you need right now is over here, the entropy column. All right, so what I do want to draw your attention to before we look up any values, I do want to draw your attention to the units. And this is going to be really, really, really important here in a couple minutes. The enthalpy and this thing, which we haven't talked about yet, Gibbs free energy, they're given in kilojoules per mole. And entropies are in joules per mole times Kelvin. So you're gonna have to divide this by 1,000 or multiply these by 1,000 if you ever go to add them together. So we'll talk about that in a moment. So I do want to draw your attention to the units while we're looking up here at the top. Okay, I want to do one of these problems, man. So let's go back and let's look at the problem we want. So we want H2O liquid turning into H2O gas. I want to see what the change in entropy is for that. Now I want you to make a prediction. We're going from liquid to gas. Do you think we're going to have an increase in entropy, a positive delta S? Or do you think we're going to have a decrease in entropy, a negative delta S? So make a prediction now. And we're going to solve for it, and we're going to see if your prediction's right. Okay, so here we go. We need to do the products minus the reactants. Now, the nice thing is, since everything has a coefficient of 1, okay, you don't have to, we don't have to multiply by anything. So we want H2O gas minus H2O liquid. Let's find those entropy values. Let's do this thing. Now, these thermodynamic charts are alphabetical by like element. So this is going to be under either oxygen or hydrogen. I don't know which. Probably oxygen. Let's go to oxygen. So there's F, P, M, N, O, and I was wrong. So it's back to hydrogen, folks. Yep, water's under hydrogen. Who knew? So we want the gas, okay, minus the liquid. So that's going to be 188.8 minus 70. We don't even need to write that down. It's going to be a positive 118.8, right? Positive. Now, did you make a prediction that we would have an increase in entropy? Hopefully, we're going from liquid to gas. So hopefully you made that prediction, right? So we took the H2O gas minus the H2O liquid. Now I want to try one that's more difficult. We want to predict this one. So I want you to make a prediction, okay? We're going from 4 gaseous particles to 2 gaseous particles. So do you think this is going to be a positive delta S or a negative delta S for this reaction? And then we're going to look them up. Now, pure elements, nitrogen and hydrogen, they are pure elements. They would have a standard enthalpy of formation of 0. And they're going to have a standard Gibbs free energy of 0 as well, but not entropy. Nothing has a standard entropy of 0. So the delta H's would be 0, but we're doing delta S's, right? So we need to look up NH3, man. So that's going to be under a nitrogen right here. We want that one. So this is going to be, I'm going to try to write this crazy thing down. So this is going to be delta S equals 2 times, you know what? Maybe I could even type this. It's going to be 2 times 192.8 minus, now we need to look up nitrogen and hydrogen. So we're going to look up N2. So that's minus, there's only 1 nitrogen, so that's 191.6. Plus, there are 3 hydrogens, so that's 3 times, now we need to find hydrogen, so we're going to scroll up to the H's, 130.7. And we're going to pop that in our calculators. Here we go. So 2 times 192.8 minus the quantity 191.6 plus 3 times 130.7. And we get a negative 198.1. And then that is joules per mole times Kelvin. Joules. So hopefully you predicted this would be a decrease in entropy. We're going from 4 gaseous particles down to 2 gaseous particles. So of course, that's a decrease in entropy. We're becoming more ordered. So hopefully you got a feel for doing those. Very similar to the delta H's, right? Okay, since you guys were so good with the delta H's, you probably like golden with this, right?